In this lecture, we will be focusing on the chain rule for differentiation. So we start off with just a quick review of the stuff from last week. You'll notice first off that remember the constant rule. We have the derivative of a constant is 0. The power rule, that you bring down the power and it becomes your coefficient, and then you subtract 1 from the power itself. If you have a multiple in front of a function, you can simply pull that multiple out and take the derivative of the function. If you have two functions of x and they are added together, you simply take the derivative separately. However, if you're multiplying them together, you take the derivative of the first times the second plus the first unchanged times the derivative of the second. And finally, if you have two functions of x that you're dividing, you take the derivative of the first times the denominator unchanged minus the numerator unchanged times the derivative of the denominator, all over quantity the denominator squared. I've given you here both the Leibniz and the Lagrange notation. For the course of this lecture, I'm going to leave the Lagrange notation up just so that we can refer back to it. There is also a sheet that you can print off of chalk if you're interested that has all of these rules and also the rules that will come from the next lecture. So let's take a quick moment and just talk about this chain rule. The chain rule is, after the power rule, probably the most frequently used rule for differentiation. That said, it takes a little bit of sort of thinking through in practice to really see how you apply it. So the chain rule applies anytime you can take a function and break it into two different pieces. So in this case, we are talking about the function f of g of x, and we could also rewrite it as f of g of x. What we do when we take the derivative of a function that can be split into, that can be re-expressed as the composite of two different functions, is we take the derivative of the first function, including that second function, and basically treating that second function like a constant or like a variable. And then we take the derivative of that function and multiply it together. This is something that I think is a lot clearer in practice. So let's go ahead and do a few examples. So here we have the function h of x, and you'll notice that none of the rules that we've already talked about really apply. We have the power rule, so we can express x squared plus 1, and the square root is a 1/2. And so we can know how to take sort of the derivative of the outside, but we don't have any rule that applies if the thing that's being raised to a power isn't just your straight old variable x. So what we want to do is we want to ask ourselves if we can rewrite this as a composite function. This is something that just takes practice to see. So what I'm going to look for is functions within this function that whose derivative I know how to take. Now I've already said that I know how to take the derivative of x to the 1/2. So I'll go ahead and say that the function f of x is going to be x to the 1/2. And I then know that the derivative of that function of x is equal to 1/2, bringing down the power as the coefficient, x raised to the 1/2 minus 1, which is negative 1/2. Now, I need to think separately about this function on the inside. So I can say that g of x is equal to x squared plus 1. And here I have two different terms added together, so I take their derivatives separately. I use the power rule on the first, I get 2x. I use the constant rule on the second, I get 0. So now we have these two different derivatives, and we need to sort of think through how we would write it as a composite function. Notice that the g of x is being square rooted. So if we were to rewrite this, we would write it as that h of x is the composite function of f and g of x. And you can think it through and actually just check that that's the case. If I took x squared plus 1 and put it in place of the x here, I would get x squared plus 1 to the 1/2, which is the function that we're trying to take. Okay, so I've sort of thought through the composite function. I know the two derivatives that I'm interested in. Now I just need to apply the chain rule. So the way that the chain rule works is that we leave the g of x in place. So here we had x squared plus 1 in place of the x. So f prime of g of x is going to be 1/2, so I'm looking up here at this derivative, times, except that I have g of x for my x squared plus 1 to the negative 1/2. So that's my f prime of g of x, times the derivative of g of x, which is 2x. And if I want to, I can simplify it, cancel the 1/2 and the 2. I get x, and I'll express this as a square root and get rid of the negative sign, x over the square root of x squared plus 1. So let's try this next one. I'm again going to think through how I can write this as the composite of two functions. I'm going to this time write f as a function of y rather than of x, just to make it clear what's going on. So as I think about this function h of x that we have here, I can break it down into two pieces. So I know that I can rewrite this cube root as a negative exponent. So I'm going to say that my f of, and this time I'll call it y, is equal to y raised to the negative 1/3 power. So what you can see here is that I've just rewritten that as a power, but I could also write it as the cube root of y. Those are the same things. I write it in this form because the power, it makes it easier to correctly apply the power rule. Okay, so that's my first function. And then I need to deal with this function on the inside, so I'm going to say that my g of x is equal to x squared plus x plus 1. I can calculate the derivatives of each of these separately. My derivative of f with respect to y is equal to negative 1/3 y to the negative subtracting 1 4/3. And that my derivative of g prime with respect to x is going to be 2x plus 1, and the constant terms derivative is 0. So now I need to combine these. I'm going to double check that I've done this correctly, that my composite function is set up correctly. So if I take f composite g of x, I'm going to substitute x squared plus x plus 1 in for the y in the function. So there I would have x squared plus x plus 1 raised to the negative 1/3 power, and I double check that that is in fact equal to the function that I'm trying to figure out. It is. It's equal to h of x. So now I'm going to apply the chain rule. So I take first the derivative of f, and I'm plugging in for y g of x. Okay, so I have here the derivative of y was negative 1, the derivative of f of y was negative 1/3 y to the negative 4/3. So I'm going to substitute in my x squared plus x plus 1 raised to the negative 4/3 power. So that gets me this first half of the chain rule. I've taken the derivative of f with respect to y, and then I've substituted in g of x for that y. And now I'm going to multiply it by the derivative of g, which was 2x plus 1. If you want to, you can rewrite that. I would generally leave the 2x plus 1 on the top, not worry about distributing. I have a minus sign times the entire function. and I'll leave the 3 on the bottom with x squared plus x plus 1 to the negative 4/3. So here's another example. This is probably a good time if you want to pause the video to see if you can work out the example on your own, and then I'll go through the solution. All right, so to get the solution here, I'm going to break this into two different functions. I'm going to say that my f of y is equal to y to the 9th, and that my g of x is equal to x minus 2 over 2x plus 1. And I can stop there because I recognize this is a quotient, and I can use the quotient rule if I want to. So I'll take the derivative of f with respect to y is equal to 9y to the 8th. And the derivative of g with respect to x is going to be equal to, I'm looking over at the quotient rule. I take the derivative of the numerator. I get 1 times the denominator unchanged minus the derivative of the denominator, which is 2, times the numerator unchanged over the denominator squared. I should probably go ahead and simplify the numerator here. I distribute the 1, I get 2x plus 1. I distribute the 2 and the negative sign, I get minus 2x plus 4 over 2x plus 1 squared. I'll do a final step of cancellation. Notice that my 2x's cancel out, and I'm left with 5 on the top. So that's equal to 5 over 2x plus 1 quantity squared. And the final step, I'm going to apply the chain rule. I look up at my derivative of the first function. I have 9 times, I'm going to substitute in g of x for y. So that's x minus 2 over 2x plus 1 quantity to the 8th times the derivative of g, which is 5 over 2x plus 1 squared. If I want to, I can go ahead and simplify this a little bit farther. I multiply my constants out. I get 45 times on the top x minus 2 to the 8th power over on the bottom 2x plus 1, and I of course add the exponents raised to the 10th power. I often find it helpful to think of these kinds of problems in more of this kind of a format where you can sort of see the substitution as it happens. So here obviously h of x would be x squared plus 2x plus 3 quantity squared. If I wanted to take dh du, so the derivative with respect to this u, it would simply be 2u. If I wanted to take the derivative of u with respect to x, it would be 2x plus 2. And so now you can sort of see why when the chain rule is written using the Leibniz notation, you get that dh dx is equal to dh du times du dx. Now this is a little bit of a simplification because you have to remember that in this dh du you need to substitute in the x. So the final step here, if you wanted to find the derivative of h with respect to x, would be to take 2 and then substitute in for the u, x squared plus 2x plus 3 times your derivative of u with respect to x, 2x plus 2. All right, go ahead and try these two on your own. Pause the video, and I'll come back in a moment. All right, so here for the first function f of x, I see two functions. I see the function on the inside here, and I see a function on the outside there. So I'm going to say that f of x is equal to u to the fourth, where u of x is equal to x cubed minus 5x. df du is equal to 4u cubed. Du dx is equal to 3x minus 5. Sorry, that's 3x squared minus 5. I put them together now. I get that df dx is equal to 4 times, remember that u is equal to x cubed minus 5x raised to the third power, times 3x squared minus 5. On this second one, I'm going to start off just by rewriting this as 2t minus 1 raised to the negative 1/5 power. So I can let f of starting over. So I can write g of t as u to the negative 1/5, where u is equal to 2t minus 1. I get that g prime is equal to negative 1/5 u to the negative 6/5. And I get that u prime is equal to 2. I now combine the two. I get that g prime with respect to t is equal to negative 1/5. I substitute in 2t minus 1 for u to the negative 6/5 times the derivative of u, which is just 2. So I could rewrite that as negative 2/5 times 2t minus 1 to the power 6, negative 6/5. So far today we've seen a number of different problems that you approach by applying the chain rule and then using your other skills from last week to find the derivative of the functions that go into the composite function for the chain rule. In this lecture, I've used sort of two different approaches. The first one where we identify the composite functions, the second one where we think more of sort of a substitution thing. It's fine using either of those approaches. In this case, for this particular problem, as you look at it, you might notice that really if you were thinking about a composite function, you're actually kind of breaking it into two different composite functions that are then multiplied together. So you could think here that u of x is equal to 2x plus 1 raised to the 5th power, and that v of x is equal to x cubed minus x plus 1, all raised to the 4th power. Now I'm going to skip some steps here, but you might want to, if you're having trouble following what I do, just pause the video, write out the composite functions fully or the substitution process fully to see it. So here the derivative of u with respect to x is going to be equal to 5 times 2x plus 1 to the 4th, so that's the outside of the composite, times the derivative of the inside, which is just 2. And the derivative of v with respect to x is going to be equal to 4 times the thing inside the parentheses, raised to the 3rd power, times the derivative of the thing in parentheses, 3x squared minus 1. So now we have two functions and their derivatives, and we're multiplying them together. Well, we know from the product rule that the derivative of g is going to be equal to the derivative of u times v plus the derivative of v times u. So I go ahead and do that. It just gets a little bit messy. The derivative of u, I'm going to combine my constants. I get 10 times 2x plus 1 raised to the 4th power times v, x cubed minus x plus 1 raised to the 4th power, plus the derivative of v, 4 times x cubed minus x plus 1 cubed times 3x squared minus 1 times u, which was 2x plus 1 raised to the 5th power. Now you're probably looking at that and just shaking your head and saying this is insanity, and that's okay. This is partially done just for the sake of example, but also so that you think through each of the different steps that are involved here. In order to simplify this function, I'm going to notice that I have 2x plus 1 and 2x plus 1 and x cubed minus x plus 1. So I can factor those out. Notice that I could also factor out a 2 if I wanted to. So that would be equal to 2 times 2x plus 1. And I look and I'm just going to take the smallest of the powers. So that's 2x plus 1 to the 4th. And again, with x cubed minus x plus 1, I look here as I'm simplifying. I say, well, that'll be cubed. That's the smaller of the two powers. So I factor those things out, and now I look at my two terms and I say, what's left? Well, I have a 5 left here. I fully factored out this term, so it disappears. I'm left with one of these. So I have 5 times x cubed minus x plus 1. I look at my second term. I factored out a 2, so I'm left with 2 there. I fully factored out this term. The second term was not factored out at all, so I have 3x squared minus 1. And then with this last term, I was left with just one of them, so I have 2x plus 1. Oh, so at this point, if I want to, can actually multiply this all the way out. So I'm going to leave the first part as it is, 2x plus 1, x cubed minus x plus 1. Both of those are raised to their powers. And now I multiply this full thing out. I get 5x cubed minus, subtract that. Minus 5x, distributing the 5 across, plus 5. I multiply all of this out. I FOIL it out. I get 2 times, this would be 6x cubed, so that would be 12x cubed. That's that. I multiply that out. I get plus 6x squared. I do the inside of the FOIL. That would be minus 2x, so minus 4x. And then finally, that times that is -1 or just -2. I can then combine like terms. I get, again, not doing anything to the first part of the expression. I'm taking my x cubes and combining them. I get 17x cubes. I have only one x squared term. I take my x terms and combine them. I get minus 9x. And I take my constant terms and combine them, plus 3. To be perfectly honest, on an exam, especially if time is an issue, I would probably leave it in that form. The worst case that's going to happen is, you know, we dock you a quarter point or something. It's just not that important at this point. You, as you're working through the simplification. So, that's sort of the devil version of this problem, but you do sometimes see problems where you're going to have to first apply the product rule or apply the quotient rule and then apply the chain rule for the functions inside of that. So here's one for you to try on your own. Go ahead and pause the video and then come back and I'll walk you through it. All right, so I look at the first term here. I'm going to call this u and call this v, and I'm going to say that the derivative of u is equal to 10 times 3x minus 2 raised to the 9th times 3, and the derivative of v is going to be equal to 12 times 5x squared minus x plus 1 raised to the 11th times 10x minus 1. And so my derivative of g of x is going to be equal to the derivative of u. I'm going to multiply my constants together. I get 30 times 3x minus 2 to the 9th. So that was the derivative of u, times v, which is 5x squared minus x plus 1 to the 12th, plus the derivative of v, 12 times 5x squared minus x plus 1 to the 11th, 10x minus 1, times u unchanged, 3x minus 2 to the 10th. We can factor things out here if we want to. I'm just going to go ahead and factor out the 3x minus 2. I take the smaller of the two powers to the 9th, and 5x squared minus x plus 1. I take the smaller of the two powers to the 11th, times, I left my constant there, 30. My second term disappeared. I was left with just one version of the third term. Plus, I was left with my constant term. I factored out the full first expression with x. I'm left with 10x minus 1 times 3x minus 2, and I had factored out all except one of those. For the sake of the example and time, I'll just leave it there, but you could have simplified that out a little bit farther. There are really two different ways to break this out. One is to use the quotient rule and the other is to use the product rule. So if you want to, you could see this as u over v and use the quotient rule. I'm going to argue that it's actually, in this case, a lot easier to see it as u times v. So here, u is simply y, and v is equal to 7 minus 3y to the negative 1/2 power. If you were using the quotient rule, it would be the positive 1/2 power. The thing about it is that this is sufficiently complex that following through the quotient rule gets fairly messy, and simplifying the quotient rule gets very, very messy. The product rule simplifies a lot more easily. So I tend in these situations to use the product rule. And the thing about the quotient rule is that the quotient rule is basically the product rule with a built-in chain rule applied to correctly get there. And the last thing I'll do in lecture today is actually show that to you. Okay, so how do we deal with this as a product rule? Well, the derivative of u is going to be 1. The derivative of v is going to be negative 1/2 times 7 minus 3y to the negative 3/2 times negative 3. Notice that that last step is because we need to take the derivative of that inside term. So there I'm now using the chain rule to take the derivative of v. I might simplify that out and get that the derivative of v, I cancel my negative signs, is equal to 3/2 times 7 minus 3y to the negative 3/2. Finally, the derivative of h with respect to y is going to be the derivative of u times v unchanged, so that would be 7 minus 3y to the negative 1/2 plus u, which is y, times the derivative of v, 3/2, 7 minus 3y to the negative 3/2 power. So if you want to, you can simplify that a little bit farther, but for the sake of time, we'll leave that there. So the last thing I want you to think about for today has to do with where the quotient rule comes from. So if I'm trying to take the derivative of a quotient, I can use the quotient rule. But another approach is to think of it as f of x times g of x to the negative 1. So if I wanted to take the derivative of g of x to the negative 1, what I need to do is apply the chain rule. I bring the negative 1 down. I get g of x to the negative 2 times g prime of x. Okay, so that's me just applying the chain rule to this second term. What I get is that if the derivative of f of x, g of x, is equal to the derivative of the top, f of x, times the bottom, but here it's g of x to the negative 1, okay, plus f of x unchanged, times, and now the derivative is this entire term right here. So that would be times negative g of x to the negative 2 times the derivative of g. So if we simplify this, notice that we have g of x to a negative power in both cases. I'm going to simplify it by going for the highest power, the negative 2. So I'm going to ask, how can I rewrite this with g of x squared on the bottom? Well, on the second term, it just cancels out, and we're left with negative f of x g prime of x. With the first term, I have to multiply this by another g of x. So I get f prime of x times g of x. And notice that if you simplify this, if you tried to split it out, you would cancel out one of the g of x's and be left with g of x to the negative 1. So all of that is to say, if you ever happen to forget the quotient rule, you can just use the product rule, as long as you're careful about how you handle this negative sign working through. All right, so that was a long lecture. The chain rule is incredibly important. It's something that can be tricky to apply sometimes and really just takes practice to gain fluency in using consistently. So that's our goal for the class.